So problem 7 and 8 from problem 35. Well, problems number 30, chapter 35, 7 and 8. 7. A student shines a red laser pointer with a wavelength of 675 nanometers through a double slit apparatus in which the two slits are separated by 75 micrometers. He observes the diffraction pattern on the wall 1.50 meters away. What is the distance between the central bright fringe and either of the neighboring bright fringes on the wall? All right, so we're using some of what they talked about Young's experiment and stuff like that. So diffraction occurs when waves pass through a narrow opening or near the edge of an obstacle. A diffraction pattern consists of bright and dark regions. Like diffraction, interference is a wave phenomenon that results from the superposition of waves, producing a characteristic pattern of bright and dark fringes. So you can mimic diffraction in a sense through interference. A common distinction between the two phenomena is that diffraction involves only a single aperture or source, whereas interference involves two or more apertures. So what they're saying here, this is more, they say through a double slit apparatus, and then they talk about the distance between the neighboring fringes. So he observes the diffraction pattern associated with the interference that goes on, you guys. For Young's double slit experiment, let me try to see what the other one is. We talked about this. Let me write a couple of formulas down that are going to be useful to us when we do this. Okay, so let me get rid of this. So we're done with 35. I'm sorry, we're done with chapter 34, rather. And let's go to 35. And let me just get rid of some things here. We're talking about Young's double slit experiment. Regarding maximums, maxima, d sine theta of n, theta n depends upon n right here, and lambda. Lambda is the wavelength, and n equals 0, comma, plus or minus 1, comma, plus or minus 2, comma, plus or minus 3, comma, dot, dot, dot. That's for maximum. And for minima, so these are bright. These tend to be bright. These are bright, not tend, they are. They're bright. And then for the mins, dark spots, dark places, quantity n plus 1 times a half, the quantity n plus a half times lambda, where n is, and they're doing it again. But it's a different dynamic. I mean, different circumstances are arising here. Talk about how the interference pattern is going to take place. So you've got that. Good luck erasing that. I don't know what's going to happen, but we'll see. All right. So, you know, that'll take us into 7 and 8 pretty well, I think, to talk about that. So they're saying here, let's just do it one more time. A student shines a red laser pointer with a wavelength of 675 nanometers through a double slit apparatus in which the two slits are separated by 75.0 micrometers. He observes the diffraction pattern on the wall 1.50 meters away. What is the distance between the central bright fringe and either of the neighboring bright fringes on the wall? So neighboring, right next to them. So you're not going to go too far away when you do this. So what we got here, there's two different ways you can just go between the two of them. Let me try to think. I already don't like the way I wrote it, but okay, that's fine as is. So we're going to say we're talking about the bright fringes, right? So we're going to go one or the other. It doesn't really matter. Tell you what, delta D, the distance between the two, is going to be delta of one of them. So delta B is the difference in the two places. So in other words, there is, when we do this, I think of this a good way to explain this, guys. Give me just one little second here to figure out what we're doing here. If you're going to look at it that way, the distance that they're apart, so you're going to have to find two different places here. I'm back, we had to kind of look at this a little bit. If you go to the Katz book to pages 1129 and 1130, they've got good discussion of this as well. This is said elsewhere in the very back of the chapter, at the end of the chapter, where they summarize some things very, very nicely. This is a very nice summary as well, found at the back of the chapter and in other places as well. And on these pages, 1129 and 1130, we've got some things we can talk about. Essentially, these are the bright fringes. I mean, here's a bright fringe, here's a bright fringe, here's a bright fringe, et cetera, et cetera. This is the central, the big one. How far apart are these? I mean, so the question they're asking is, how does that all work out? You know, how far apart are these? So, from Similarity of Triangles, this is theta 1, right here, and that is also theta 1. So that's going to be kind of interesting. From here to here, I can find out what's going on right there as far as what that distance would be. We'll call it delta y if you wish. And we kind of go from there. And we're looking for the first bright fringe. Here's the central fringe, and here's the first bright fringe. Let's figure out what's going on here. Well, they gave us some data. I mean, this is right here, the length from here to here, or the distance from here to here is, I think it was 1.5. And then the difference between these two, so they told us L was 1.5 meters, and that small distance was 75 micrometers. The wavelength of the light under consideration is 675 nanometers. D sine theta 1. Now we know that D let's see, D sine theta 1. I want to just get this straight. For some reason, that D does not really appeal to me. Let me think. It does. It's actually right. I just wrote it wrong. Just write this a little bit bigger. This is the 90-degree angle. Forgive me, guys. This is the 90-degree angle right here. Right here is the 90-degree angle. That's theta 1, and that's D. So delta D over D. This is the hypotenuse. That's the hypotenuse. These are the slits. That's D. Opposite over hypotenuse is the sine. And this will help us do a lot of stuff, I guess you could say. So I guess there's a lot we can know, a lot we can find out. We know that if you figure out the path, the difference between the two paths, D sub B and D sub A. D sub B and D sub A, the difference between the two paths, this one's the long path, and this one's the short path. Long minus short, they'll differ by one wavelength, because they're going to be in phase, and they're still going to be bright over here, but they got to differ by one wavelength. So delta D is going to be one wavelength, and because we wanted the one that was closest, so delta D is one wavelength, that's lambda. This guy is D, and that's sine theta 1. Okay, not too bad at all. Then you can basically say that the sine theta 1 is lambda over D. Theta 1 is the inverse sine of lambda over D is equal to the inverse sine of, they said what they say it was. It was 675 nanometers divided by D, which is 75 micrometers. It's not exactly a huge quantity in its own right. That's on the bottom, but there is a difference. When you get the inverse sine of this ratio, this is an interesting ratio in its own right, you get actually 10 to the negative 6. You can also get 10 to the negative 6 right here if you just move it over 3 places. 0.675 times 10 to the negative 6, 75 times 10 to the negative 6. 10 to the negative 6 divided by 10 to the negative 6 is out of there. It's 0.675 over 75. That ratio is the sine of theta 1. Get the inverse sine of that, and you are going to get, let's just see what I've got. I got here the notes as well regarding that. You're going to get a bunch of things here. You're going to get 0.51, 0.51567, 0.51567 degrees, which is equal to 0.009 radians. Okay. Now I'll tell you what. We can mimic the whole thing right here. We can say this is it. Theta 1's right here. This is big L on the bottom right here. This is big L. This is the length from here to here. That's big L. That's delta Y. I got news for you. Delta Y over big L is equal to the tangent of theta 1. Delta Y is equal to L times the tangent of theta 1. This is 1.5. This is the tangent. Take your pick. I mean, just make sure you're using the right functionality on your calculator, you guys. I'll use radians. There's a reason for that. Radians actually resemble the actual ratio of the lengths. If you multiply by 0.009, if you just didn't even take tangent, when 0.009 times 1.5, you get 0.0135. And it should be right about pretty close to what it is. Let's play it rigorously though, just in case. So what we have here is, let's make sure everybody's on the right page. We got that right there. And this. Okay, sounds good. the end of all that, 1.5 times the tangent of 0.009, 0.0135 meters, .0135 meters, which is 1.35 centimeters, which is 1.35 times 10 to the negative 2 meters. Does it really matter? Well, it depends how they ask you to answer the question. The way they ask us is how we're going to answer it. But that's the answer. I already told you that you can almost ignore the tangent. When it's very, very small angles, the tangent and the sine roughly equal the angle if the measurement under consideration is radians. The radian measure of angles for very, very small angles is very, the radians measure for angles that are very, very small is very, very close to the sine of that angle, is very, very close to the tangent of that angle, if they're small. In radians. In radians. Theta is approximately equal to the sine of theta is approximately equal to the tangent of theta. For very small. In radians. For very small theta in radians. So, it's all right. Put it in there. Get it right. Don't have your calculator on degree mode when you're using radians. You're going to be an invitation for trouble. So that's the end of that. That's number 7. 8. Take the same argument, I guess. 8. Monochromatic light is incident on a pair of slits that are separated by 0.2 millimeters. The screen is 2.5 meters away from the slits. A and B here. A, if the distance between the central bright fringe and either of the adjacent bright fringes is 1.67 centimeters, find the wavelength of the incident light. Great question. B, at what angle does the next set of bright fringes occur? So you have to open it further. At what angle are the next set of bright fringes? So the way we drew this, these are bright fringes right here. The next one would be here. Here are the first ones, and then you get other ones. So I'll tell you what, let's leave that up there. And let's leave a lot of this up there, actually. And let's see what we can do. Let me at least take care of this. Basically the same kind of argument. Here, they're telling you what we just found for problem number 7 was the separation when they gave us other things. Now, do. So for the first one, we found the separation, or at least the distance to the next one. Here for the first one, they said they gave us the distance. They wanted us to find the distance to the next one. We found it. Now, they already gave us the distance to the next one. They didn't give us that information to begin with, but now they do. All right, I guess we'll take it the same way. In this case, this whole different dynamic, but a lot of the same mathematics is going to take place. The difference in the path, you guys, is delta B minus delta A. The difference in the path is the difference in the path, delta D, is dB minus dA. Delta B is d sine theta n equals n times lambda. Well, for the first ones under consideration, n is 1, that's theta 1, so delta D is going to equal 1 times lambda, is going to equal lambda, is going to equal D sine theta 1. So, I mean, that's pretty important. So what happens is, D, they gave us a bunch of stuff here. Let's see what we got here. Well, they told us a number of things. They already told us what delta Y was. They gave us delta Y in this case. And they're asking, what's the angle? Well, I'll tell you what I'm going to do. They gave us delta Y. Sine theta 1 is delta Y over L. It's not the sine in this case. In this case, it can be the tangent. Not a huge difference, but there's nevertheless a difference. Let's do it right. Tangent theta 1 is the rise over the run. The run is L, the rise is delta Y. Theta 1 is inverse tangent so we got all that. Let's, we're going to get to this. Forgive the delay on that. Stay tuned on this one, as they say. It's going to be d sine, it's going to be d sine theta 1. We'll get there. Let's just find theta 1. Theta 1 inverse tangent, as we said, of delta Y over L. What did they say here? They said it was 1.67 centimeters, which is the same as 0.0167 meters. Here, the units got to agree. Units have to agree, you guys. There can't be a disparity in the units. 1.67 centimeters is 1.67 centimeters is 0.0167 meters. The length is 2.5 meters. These aren't really big numbers. I mean, the ratio is not going to be a big number. Get the inverse tangent here and see what happens. So when you actually do this, you get 0.38273. That's degrees. In radians, that's a different dynamic. I mean, it's a different number in radians. Radians are the best, but right now we got degrees. It should work if we got everything set. It will work, rather, provided your calculator's on the mark with what you got to do. So what did they tell you? They told you that D, that was delta Y. They told us that D was 0.2 millimeters. 0.2 millimeters is 2 times 10 to the negative 4th meters. 2 times 10 to the negative 4th meters times the sine of what we just found. We used the tangent function to find this angle, the inverse tangent that is, utilizing the reality of what the tangent function means, and we found the degree manipulating what tangent means. Remember now, this whole process is one of You know, you're basically going from here, and you got here, and that right triangle, they already gave us what delta y was. They already gave us what L was. So here's L, here's delta y, and there's the angle you're trying to find. Which incidentally is the same as this angle. Which makes it all possible, because if they're the same angle, I can look at what I know here, which is going to have to be the same length as the wavelength, and what they gave me here, which is 1.67 centimeters. And, I'm sorry, this is 1.67 centimeters, and this right here was 0.2 millimeters. Obviously not drawn any kind of good scale, you guys. Sorry about that, but okay, do the job. I mean, you get to here, that's what lambda's going to be. When you do it, you're going to get 1.336 micrometers, which is the same as 1.336 times 10 to the negative 6 meters. You know they both mean the same thing, guys. For very small angles in radians, where theta equals S over R, theta is approximately equal to sine theta is approximately equal to tan theta. This approximation does not apply when theta is expressed in degrees. This doesn't work when you're doing, if I would have converted this theta into radians, I could have used sine theta 1 is approximately equal to sine theta 2 is approximate, forgive me, I could have used sine theta 1 is approximately equal to tan theta 1. So sine theta 1 is approximately equal to tan theta 1 is approximately equal to theta 1 if theta 1's in radians. So it's so important to know the radians. So it came out. That's what you got. So what happens in the next situation? Again, this is the numbers probably shouldn't be too big. It should be okay. That's A. Let me run over here for, now this all has been, guys, we switched over. We've been doing problem 8 right now. I just left a lot of the drawing up there because it applies. We've been doing problem 8. So let's get 8B. They're playing the same game with us, guys. Let's find the angle. To get a bigger fringe, you're going to have to get this guy to go from here, to go up here, and from here to go over there. It's a new dA dB. You know, here's the new dA right up here. Here's the new dB. This guy right here, and then you figure out what's going on. It's the same kind of argument. Only here, the bright fringe is not going to be after a path difference of 1 lambda. It's going to be, instead of a path difference of 1 lambda, which is what we did for 8A, we're getting a path difference of 2 lambda for the next bright fringe. So if that's the case, play the math as we have to play it. D sine theta n yeah, there's going to be a 2 lambda path difference. This tells us what the path difference is. Okay. We know that the sine of theta sub 2 is going to be 2 lambda over d. Theta sub 2 is going to be the inverse sine of 2 lambda over d. What is that? Well, we already did something about this, guys. Lambda was 1.336 times 10 to the negative 6. slits are 0.2 millimeters apart. That's 2 times 10 to the negative 4 meters apart. Okay. That's sine theta 2. That's the difference. Okay. Get the inverse sine. Sine theta 2 is the inverse sine of all of that. It ain't much. I mean, it's not. It's big. It's twice as big an angle, roughly, as what we had before, but it still ain't much. 0.7655. 0.7655 degrees equals 0.01336 radians. It's pretty interesting. Very interesting how that all transpired, actually. What's going to happen is it's going to be 1.336 times 10 to the negative 2, which is 1.336 times 10 to the negative 2 is 0.01336 radians. So that's pretty big. Here's your angle. Here's your angle. As we said, if the degrees are, if you're using radians, theta is about equal to sine theta is about equal to tan theta. They're all about equal to each other. If it's really small degree measures. I didn't say small numbers. I said the degree measures under consideration. If they're very, very small, they should be right, which equates to small numbers, but they got to be really, really small. So that's it. I mean, what were they saying here? So that's going to happen at the end of that entire day, you guys. You got this. They asked on this, I think they just wanted the angle, right? The angular displacement. At what angle does the next set of bright fringes appear? There they are. How far away are they from the central fringe? I guess I would just use this formula, you guys. I'd say I'd use there you would not going to be able to do it. You'd have to basically use this formula, but it wouldn't be theta 1. You'd use what is the delta. What is delta y? Delta y would be stuff we had done earlier. We could, nobody asked us, so forgive me for even going there, guys. What the heck, might as well. Delta y here over d, right, that's going to be equal to delta y over the, so let's see exactly what we would say on that one. It would be delta y over L rather, forgive me. Big triangle, find the tangent, and that's the tangent of theta sub 2. Now nobody asked you that, but the delta y here, delta y sub 2, for example, would be L tan theta sub 2. Take theta sub 2, get the tangent, multiply by capital L, you'd find the displacement from the central fringe that way. Okay. All right, that would take us through 35. I will start later, you'll see it soon, chapters 37 and 38. It's a total of 4 problems. We should be able to get through them pretty good.